There we are. Okay. Last lecture, we talked a little bit about numerical series, and we established the root test. Okay, remember the root test lets us take this limb soup of the nth root of the absolute value of the coefficients of a series, and that determines if the series converges or not. So today we're going to apply the root test to power series. We get a lot of consequences today out of not too much work, just using things we've already proved. And a lot of this is we're going to establish uniform convergence, and we're going to go back to theorems from last semester that we had on uniform convergence for integration and differentiation. Okay, so let's get started with the definition. Let's let AN be a sequence of real numbers. And suppose A is a particular real number. And just for ultimate generality, let's suppose M is a natural number. Then the expression sum n equals m to infinity of an times x minus a to the n is a power series with center A. Okay. I hope this is familiar to everybody. Please jump in if you have any questions.
In this situation, are natural numbers including 0?
Yes. This semester, our natural numbers always include 0.
Okay.
Last semester, they did not. So, okay, this center thing, that doesn't really matter. The center just shifts the behavior of that series left or right. Okay, if it's a positive A, then you're shifting it to the right. If it's a negative A, then you're shifting it to the left. The other thing that doesn't really matter is the M here where we start. We could always take that M to be 0 and just pad some of the sequence with zeros. Okay, so we might as well just assume that A is 0 and M is 0. So for convenience, we will only study, so we only consider these guys. The sum from n equals 0 to infinity, an x to the n, and I will just write that as a summation sign and then an x to the n without saying any indices. Okay, so when I write that, it's assumed n goes from 0 to infinity, and you don't have to assume the center is just 0. Okay, everybody agreed we're not going to lose anything here. This is just going to save us some writing. Okay. Our first question is, where do these converge? So these are, well, okay, so you can't say a power series is a function because where it doesn't converge, it's not a function. So we have to be a little bit careful here. We're going to define the set where it converges, and then we can say that on that set it's a function. So that is why we do this. So given a power series of this form, we define a set D for domain to be the set X such that that series converges. Okay. So since the power series converges on the domain, on the set D, we can take it to be a function there. So that's D into R. Okay. Now, let's introduce terms for the partial sums. When we looked at series, our partial sums were S sub k, so we'll do the same thing here. So we're going to define S sub k of x to be the sum from n equals 0 to k of a sub n, x to the n. Where do those partial sums converge?
Isn't it just everywhere since it's finite?
Yeah, it's everywhere. The sum is finite, so what can you say about the partial sums?
Well, they're finite, but they're not necessarily bounded. I don't know the answer. I'm just adding a thought, so maybe someone else can figure it out.
We have a special name for these types of functions.
A polynomial?
Yeah.
Okay.
they're polynomials. Okay? And now, we're going to define S of x to be this function. So S of x is the sum. I will write in the indices here. Okay. What do I mean by this limit? Well, at least on D, well, okay. So what I should say is for x in D, right? Where the big power series converges, it's clear that it's the pointwise limit. So when we write limit like this, we always mean pointwise limit. Okay, it's clear it's the pointwise limit of the partial sums. Why is that clear? Well, I mean, if you fix an x, if our power series converges, then clearly, I mean, just by definition, those partial sums converge to it, because that's what it means for the series to converge in the first place. Okay? Okay, so we've defined power series. We've defined their domain, that's just the set of points where they converge. And we've got the partial sums. Okay? Now, you might remember from Calculus 2 that we have these intervals of convergence and radii of convergence. And we're going to, actually, before we define those, we're going to see what they are. So this is our first result. Theorem. Okay. You've got a sequence AN, that's the sequence of coefficients. And we're going to define this capital R thing. It's the reciprocal of the limb sup in the root test. Okay. Now, we have to do something a little bit special here. That limb sup might be infinite, and it also might be 0. So we are going to allow ourselves, just for the purpose of this theorem, to divide by infinity or to divide by 0. We'll be clear that we don't really mean that we're doing this, we're just interpreting R that way. So where R is interpreted, 1t, as being 0 if the limb sup is infinity, and infinity if the limb sup is 0. Okay? Okay, so that's all just the definition of R. Here's the actual content of the theorem. That's your radius of convergence. So the series converges in the open interval from -r to r, and it diverges outside the closed interval. Oops. Outside the closed interval from -r to r. Okay, what this theorem does not say is what happens at -r and at r. That just depends on the series. So this theorem narrows it down. You're your interval where you converge is going to be one of 4 intervals. All right, these are the 4 possibilities, because for each of the 2 endpoints, you could either converge or not converge. So this theorem proves that it really is an interval of convergence. And it narrows it, narrows it down to one of those 4, but it doesn't say which one of those 4. Okay? Any questions before we prove it? No? Okay. We've already done the hard work, which was the root test. Now we're just going to look at a particular point x, and see what the root test tells us about this power series. Okay, and you can, maybe see this in your head, although because of the limb soup, we're going to write out some details, so we're agreed that it works. Okay. We are going to look at what the root test, this is what we care about, is what does the root test say about our power series? Well, the terms of our power series are an x to the n. So there we go. And the root test says, take the absolute value and take it to the nth root, and take the limb soup, okay? Let's write out what a limb soup really is. A limb soup is a limit of a supremum of the stuff but just the tail of it. Okay. Now, what we can do to simplify this is that we've got this x to the n, and then the whole thing's raised to the 1 over n. So we can split this up, absolute value a n to the 1 over n, and then absolute value x to the n to the 1 over n, which would just be absolute value x, okay? And now we're thinking about x as fixed, so the x can come all the way out of the supremum, and we get why do we stop there? Hold on. And go all the way out of everything. Let me get that. Good. Now that is literally the limb soup from the root test of that series. And in fact, that quantity is that. Okay, now R is the reciprocal of that quantity, so this whole thing is the absolute value of x over R. Okay. By the root test, our series converges for, well, when this thing is less than 1, and diverges when it's greater than 1. I mean, that's the end of the proof. Any questions? Let me go get these motion lights to go on again. Okay, there we are. Okay,
I have a question.
great.
So here, you're letting R be interpreted as infinity or 0. So how does that apply to the result at the end?
Good point. So in those cases, you just have to double check. If the lim sup is 0, so if that thing is 0, then we always converge. Okay? Because just that quantity will be 0, and that's the root test quantity. If the lim sup is infinite, then this theorem, if the lim sup is infinite, this theorem will never tell us that we converge. Okay? Because this lim sup will be infinite, and so will never be less than 1, according to the root test.
Okay, thank you.
But yeah, thank you for pointing that out. You really do have to consider that case separately, and especially before you go dividing by R right there. Okay? Okay, good. So this theorem says where you converge is an interval. We already mentioned that. It's one of these 4 intervals. So therefore, D is an interval. D, remember, is where the power series converges. This is called the interval of convergence. Okay. R, I'll give you two reasons here. We haven't used this kind of term, but you can talk about intervals as having a diameter. I guess we've talked about diameters of sets before. So if you talk about the diameter of this interval, it would be 2 times r, so it makes sense to call r the radius. So r is the radius of convergence. Now, if you've taken complex analysis, you'll know that when you study these on the complex plane, that interval of convergence turns into a circle, and the radius of convergence is literally the radius of the circle. Okay, so that's where the term radius really comes from, but we can justify it here as being the radius of the interval. Okay. Now, our next result is where all the heavy lifting gets done. So we've got intervals of convergence. Now we want to get uniform convergence. So if your power series has radius of convergence r, we're going to be a little bit funny here. We're going to pick a real number between 0 and r, little r. And now we're going to look at the sequence of partial sums, but remember that's a sequence of functions. And our claim is that we converge uniformly to S of x on the closed interval from minus r to r. Good? So this theorem will never tell us what happens at the point capital R, but for any point smaller than capital R, we can take that to be our little r, and then we'll have uniform convergence at that point. We'll have uniform convergence in neighborhood of that point even. Okay, let's let little r be given. Now, since r is within the radius of convergence, maybe I should have warned you before we just jumped into this proof. The last theorem, the proof was basically trivial. It was just use the root test. This proof, there is a little something to it. We're going to use some Cauchy stuff. We're secretly using a thing called the Weierstrass M-test, which we didn't cover. That's why it's secret that we're using it. It's snuck in here. and we don't explicitly call for it. But anyway, there is some stuff going on in here. Okay. Since R is within the radius of convergence, the sequence TK, now that's there's no x's in there. That's a sequence of real numbers. That's not a sequence of functions. Defined by this is the sum from 0 to k. That's like the partial sums sk. But now instead of summing ANR to the n, we're going to sum the absolute values. So let me just, as an aside, right over here, what SK of R would be. Okay. Why does this converge?
I can't think of a reason why it converges, but I do have, I think I have, I feel like it doesn't converge because couldn't I pick A n to be, let's say, 1 and minus 1, and then R is 1, and then it would be 0, you'd be adding 0, 0, 0. You're gonna, I guess that doesn't converge because it's oscillating. Never mind.
So if that's your sequence AN, then what's your radius of convergence?
Okay, I see, because the R's depend on what's chosen for the A's.
Yeah.
Okay.
So in Daniel's example, if AN is minus 1 to the n, then your capital R would just be 1. And now your little r has to be smaller than 1. And you put a little r smaller than 1 in there, and now all of a sudden you converge. Okay. So this actually converges by the root test. And let's just look at what the root test wants us to do. Yeah. The sequence of partial sums converges because the series converges. So we would want to look at the limb sup of AN R to the n to the 1 over n. But we already looked at this. And we found that actually, if instead of little r in there, you had capital R, then this limb sup would be 1. That's how capital R is defined. Okay? But we have something smaller in there, so we are going to get something smaller than 1. Okay? So we've just shown if we summed forever, we'd converge. That means that these partial sums converge as a sequence, because that's the definition of an infinite series converging. Okay? Now, since the sequence converges, it satisfies the Cauchy condition. Okay. What is the Cauchy condition? Well, given any epsilon, blah, blah, blah. Let's write out the blah, blah, blah. Given any epsilon, there is some natural number, I'm going to call it capital K this time. Okay, so that if, and now we're supposed to take two terms of the sequence, I'm going to use the subscripts L and K, and we're allowed to assume that one of them is greater than or equal to the other. I mean, they have to be in some order. So I'm going to say L is at least, little k is at least capital K. Then the difference between TL and TK is smaller than epsilon. Okay, but we can write out what that difference is. One of them is the partial sum to the first, well, up to the kth term. The other one is the partial sum up to the lth term. And I assume that L is at least K, so the difference here is the K plus first to the lth term okay? And now you see we don't actually need that absolute value outside anymore. Because it's just a sum of positive terms. Good so far? Now here's the thing, we don't care about this sequence at all. We care about the partial sums. We care about the S sub K and the S sub L. Okay? But these are an overestimate on the S sub K and the S sub L, and so these being less than epsilon is all we need. Okay, so let's do that now. What do we want? We want uniform convergence in this interval minus R to R. So we're going to look at any x in there. Okay. And any indices L greater than or equal to little k greater than or equal to big K. Okay. What do we get? At that point for these indices, we want to look at the difference between the function SL at x and the function SK at x. Okay. Once again, those are both partial sums, so their difference is the terms that are in one and not the other. Oops, but there's no absolute value now. Okay. Now, that's the absolute value of a sum. So that's less than or equal to the absolute value. Sorry, that's less than or equal to the sum of the absolute values. And now, how did we choose x? The absolute value of x is less than or equal to r. Okay? So this sum is less than or equal to the same sum if we replace the x by r. And now I hope you see that that is the same sum as we had the line above, which is less than epsilon. That's it. We established uniform convergence. Just remember back to what uniform convergence is. For any epsilon, oh, I'm sorry. This doesn't quite look like how we established uniform convergence, does it? This is the Cauchy version of uniform convergence. Okay, so for any epsilon, there is a capital K, so that for any indices, L greater than or equal to little k greater than or equal to capital K, the difference between any two of these functions is less than epsilon. Okay. Well, since we already know this sequence of functions has a pointwise limit, the fact that the difference between any two of them is less than epsilon means that the distance between any one of them and the limit is also less than epsilon.
Can you repeat that? Explain it again.
So this implies, this is just a Cauchy thing. Just like Cauchy for sequences. That's what I was trying to say.
We could just get that by changing the epsilons to epsilons over 2 and doing a triangle in the bottom.
Yeah, well, okay, so how does this come out of the triangle inequality?
Well, I was just thinking, or wait, no, never mind, that one. Because we don't have S of X, we have S of something else. Never mind.
Oh, okay, sorry. I just had a mental break for a second there. Forgot how this argument works. We have S sub L of X. This is the triangle inequality argument that I'm not writing right here. No, that's not right. Oh, you know what? It's the it's the other one. I'll tell you what, let me finish the lecture here. I realized that I didn't put the details of this Cauchy thing at the end. Let me finish the lecture, and I promise I will have that explained better in the lecture notes, okay? Okay. Now, we are going to summarize the implications of this theorem in 2 minutes. Okay, so the way we remember this theorem is inside the radius of convergence, we have uniform convergence. Okay, at the endpoints we don't know, but inside we definitely do. That's this little r has to be less than capital R. Okay? So now, all of our partial sums is a polynomial, hence continuous. This implies that our power series is continuous inside the interval of convergence. Okay, so we need that R thing. Yeah, Daniel, I see your question in the chat. I'll try and answer that in the lecture notes. Let me just finish the implications here. The other one, we have to think back to last semester now, because last semester was when we did differentiation and integration of real valued functions, and we studied some uniform convergence of sequences of functions last semester. And one of the things we saw was that since the SK are integrable, S is integrable. And even better, the integral of S is the limit of the integrals of the SK. Now in Calculus 2, you learned this as term-by-term integration. Because you know how to integrate those polynomials SK. You integrate a polynomial term by term. And so this says the integral of the whole power series is the limit of those, and so it's just the term-by-term integral. The other thing we get out of this is differentiability. So in Calc 2, you learn this as term-by-term differentiability. So the derivative of a power series, you get it by taking the derivative of every term of the power series. Now, if you remember, and there's no shame if you don't remember this, when we did differentiation and uniform convergence back in the fall, this was the theorem that had a bunch of hypotheses, okay? So to actually justify the term-by-term differentiation, we do have to check that we have all those hypotheses from that theorem. It's true, and we do have them, but obviously we don't have time to do them today. So look in the lecture notes that I will be posting this afternoon, and you'll see how we satisfy all the hypotheses of that theorem. Okay, sorry for running a little bit over, and have a great weekend, everyone, and I will see you on Monday.